Let's have a look at this question. In this question, they're asking us to find the maximum and the minimum of some function of x and y, namely x squared plus 2y squared, subject to the constraint that x squared plus y squared must be equal to 1. So to do this, we're going to solve this by using the method of Lagrange multipliers. So the first thing I'm going to do is I'm going to write down the functions, the function that I'm trying to maximize or minimize, and then the constraint as well. So let f of x, y be equal to the function that I'm trying to maximize and minimize, which is the function x squared plus 2y squared. And then I'm also going to write down another function, g of x, y, which is essentially the constraint. So I'm going to take this 1 on the right side of the constraint. I'm going to move everything over to the other side of the equal sign. And I'm going to write that down, and I'm going to call that g of x, y. So that's going to be x squared plus y squared minus 1. So again, the reason that this shows up as a minus 1 is I've moved everything over to the left-hand side, and I've just called everything that's on that left-hand side. I've given a new name. I've called it g of x and y. Okay, so I have my two functions here, and I'm going to build my new function, which I'm going to call capital F x and y. And the way I'm going to build my new function is I'm going to take my my f of x, my little f of x, the thing that I'm trying to maximize or minimize. I'm just going to write down x squared plus 2y squared, and then I'm going to subtract off some variable lambda times this new g thing that I created, which is x squared plus y squared minus 1. Okay, so this is going to be kind of like my master function here. And to use the method of Lagrange multipliers, what I'm going to do is I'm going to take the partial derivatives of this capital F function, this new function, with respect to x, y, and lambda. So let's go ahead and do that. The partial derivative of f with respect to x is 2x minus 2 lambda x, coming from here. The partial derivative of x with respect to y is 4y minus 2 lambda y. And the partial derivative of f with respect to lambda is just negative x squared plus y squared minus 1. Now, the second part, or the next part of the method of Lagrange multipliers is to set these partial derivatives all equal to 0. So the first equation that I'm going to get is that I want 2x minus 2 lambda x to equal 0. The second equation is going to be 4y minus 2 lambda y is equal to 0. And the third equation that I need to solve is going to be negative, I guess I should do this, negative x squared plus y squared minus 1, all in brackets here, is equal to 0. So I need to solve equations 1, 2, and 3 for x, y, and z. So the first thing I'm going to do is I'm going to let's solve equation number 1. So from equation 1, we can see that dividing both sides of equation 1 by 2, I end up with x minus lambda x is equal to 0. If I factor that, I get x, 1 minus lambda is equal to 0. So the only way that this equation can possibly be true is if x equals 0, because if x equals 0, this whole equation is 0, or if this is 0, if the 1 minus lambda is 0. And of course, if the 1 minus lambda is 0, that means lambda must be 1. So if lambda is 1, this bracket is 0, or if x is 0, this first part is 0. In either case, this multiplies and gives me 0. So I'm going to have two cases here. Either x is 0 or lambda is 1. So let's do a couple separate cases. So case 1 is that x is equal to 0. So let's just assume now that x is equal to 0. So if x is equal to 0, I can put that into equation 3. So into equation 3, I find that, well, the first thing I can do with equation 3 is I can divide both sides by negative 1 or multiply both sides by negative 1. Either way, this negative goes away. And if I substitute in this x equals 0 into equation 3, I'm left with y squared is y squared minus 1 is equal to 0. Let's write that down a little bit cleaner. Y squared minus 1 is equal to 0. So what that would mean is y squared has to be equal to 1, which means y has to be equal to plus or minus 1. So if x is 0, that must mean y has to be plus or minus 1. So now that we know x is 0 and y is plus or minus 1, I can actually plug this into equation 2. So sub case 1, let's pick one of these values for y. So y is equal to 1. And if I put that into equation 2, so I know I have now chosen that x is 0, because that's case 1, and sub case 1 is that y is 1. So x is 0, y is 1. So let's plug that into equation 2, and I get 4 minus 2. I don't know what lambda is yet. Y is 1. I get that 4 minus 2 lambda has to equal 0, and what that means is that lambda is equal to 2. So there's my first solution. X is 0, y is 1. So solution 1 is that x equals 0, y equals 1, and lambda equals 2. All right. However, we made this choice that y is equal to 1, but we could have chosen that y is equal to negative 1, so that would give me another subcase. Again, I'm still under the assumption that x is equal to 0, so this is subcase 2. Y is equal to negative 1. This was my other choice for y. In which case, I'm going to put this into equation 2. And what do I get? What do I get when I sub y is negative 1 into equation 2? I get negative 4 plus 2 lambda is equal to 0. And if I solve this for lambda, I again get lambda equals 2. So my other solution, solution 2, is x equals 0, y equals negative 1, and lambda equals 2. Okay, so I have two solutions so far to this system of equations, but remember, all the way back in my first step here, I could have chosen, instead of choosing x equals 0, I could have chosen that lambda equals 1. So let's do case 2 here. Case 2. Instead of choosing x is 0, let's choose that lambda is equal to 1. Okay, so if lambda is equal to 1, I'm going to use that in equation 2. Into equation 2. And what do I find? If I use that lambda is equal 1, I put it into equation 2, I get that 4y minus 2y is equal to 0, which means that 2y is equal to 0, which of course means that y is equal to 0. So if I choose that lambda is 1, I'm forced to admit that y is equal to 0. Now that I know lambda is 1, y is 0, I can put these into equation 3. Put these into equation 3, multiply both sides by 1, of course, or negative 1, and I get that x squared plus y squared, and I'm admitting that y is 0 in this case, so x squared plus 0 squared minus 1 is equal to 0, which must mean that x squared is equal to 1, which must mean x is equal to plus or minus 1. So that gives us two other solutions. Solution 3 is that x is equal to positive 1, y is equal to 0, and lambda is equal to 1, or solution 4, which is x is equal to negative 1, y is equal to 0, and lambda is still equal to 1. So these are the only four solutions we have for our system of equations. And now what the game is we need to actually figure out what our value of the function we're trying to actually find the maximum minimum of, what the value of that function is at these points. And see which one is the biggest and which one is the smallest. So let's evaluate f at the, so from solution 1, we have x equals 0, y equals 1. From solution 2, we have x is 0 and y equals negative 1. From solution 3, we have x is equal to 1, y is equal to 0. And from solution 4, we have x is equal to negative 1, y is equal to 0. So if we plug these into the function, when x is 0, that gives us just 2y squared. So 2y squared in this case would give me, so this would be 0 squared plus 2, 1 squared, which is equal to 2. Same thing if I plug in negative 1, would give me 0 squared plus 2 negative 1 squared, which again is 2. If I plug in 1, 0, I get 1 squared plus 2 times 0 squared, which is equal to 1. And if I plug in negative 1, I get negative 1 squared plus 2 times 0 squared, which is equal to 1. So in this case, the max of f is equal to 2, and the minimum of f is equal to 1. And notice the one thing that is kind of interesting, and you should probably double check whenever you do constrained optimization, is to notice that all of these x and y values that we found, the solutions that we found, notice that if you do x squared plus y squared, you get 1. So 0 squared plus 1 squared is 1, 0 squared plus negative 1 squared is 1, 1 squared plus 0 squared is 1, negative 1 squared plus 0 squared is 1. And of course, that has to be true because our constraint says that we always wanted to make sure that x squared plus y squared was always equal to 1. And indeed, all of these points have the property that x squared plus y squared is equal to 1.